Exactly. Thank you. And I'd like to thank the organizers as well for giving us all an opportunity to be here in the beautiful Cargèse. And now I will go back to, again, to the experiments, I would say. So that's going to be for electric thin films. Mostly we'll talk about for electric heterostructures, where we can kind of observe these unusual effects that seem to help to decrease the effects of the polarizing field. So it will be mostly the work that I did as my PhD work at ETH Zurich. And then at the end, I will give a small, let's say, outlook teaser from what I'm doing currently as a postdoc in the Laboratoire Elzbieta, close to Paris. So, I mean, I guess you already, this morning, there were many talks mentioning ferroelectrics, so I don't have to go through it in such a detail. But the idea is that in my work, we will consider perovskites, so ABO3 perovskites. And if you think about cubic peroelectric perovskite, you will get polarization if you displace cations with respect to anions. And then if, let's say, this middle cation will move upwards with respect to the oxygen cage, you will get polarization up. And if it moves downwards, it will be the polarization down. So this is our ferroelectric, non-volatile, two remanent states. And the key concept here is that, of course, we can use external electric field to switch in between the two. And that's the idea behind all the memories written with ferroelectrics. Unfortunately, there are still a few challenges remaining that kind of prevents the integration of such ferroelectrics into devices. And I think what is very kind of annoying in ultra-thin regime, when we grow our films very thin, which ideally, of course, we want for the devices, the problem is that the polarization is going down. So already in BTO, around what 20 nanometers, you see that the polarization is going down. And that's because there are these bound charges at surfaces that will never be fully screened, even with metallic buffers, because of the screening length. And we will end up with this depolarizing field fighting this polarization and kind of minimizing it. And in extreme cases, I think when we go below 2 nanometers, 4 unit cells usually in typical ferroelectrics, we lose this polarization completely altogether. So that's something that we call critical thickness for polarization. It means that below this critical thickness, the material just prefers to stay peroelectric rather than ferroelectric. And once again, of course, this is not great because now we have this wasted volume of the material that has no functionality. And so far, there have been some material-specific solutions to overcome this problem, but there's really not a good way to get rid of this depolarizing field. And for my work, we kind of got a bit inspired by how domains form naturally in ferroelectrics and ferromagnets. So you must have all seen such beautiful flux-closure domains forming naturally to minimize magneto and electrostatic energy. While mostly known for ferromagnets, they also exist in ferroelectrics on both mesoscale and atomic scale. So that's clearly seemed to be beneficial for the system. And in fact, if you have a closer look, there's always this in-plane polarized area and out-of-plane polarized area. That's the kind of the motive of flux closure. And that was the idea of this work, kind of thinking of, can we somehow put an in-plane ferroelectric and out-of-plane ferroelectric in hopes that this will help to, fight the polarizing field? Doing is to grow something that's mostly in-plane polarized. On top of that, grow this out-of-plane polarized film in hopes that there will be no critical layer or so-called dead layer. And the way you can achieve in-plane polarization, because in fact most of the typical ferroelectrics like BTO, PTO, PZT, they all are out-of-plane polarized when grown up epitaxially. And it's quite rare to come across something that has purely an in-plane polarization. To achieve that, one can look into epitaxial strain. So of course we can strain the unit cell in the plane, but typically one ends up with some A to C domains, so still some coexistence. One has some A super domains with different polarization directions, so it can be messy. Another route would be to consider electrostatics. So these are the famous dielectric ferroelectric superlattices when we have lead titanate, which is ferroelectric, and STO growth in huge periods. And essentially what happened is that STO is dielectric. It cannot really screen the out-of-plane polarization of PTO, and then PTO is kind of forced to go in plane. And in that way, we can electrostatically push the polarization in the plane of the film. But now, as much as I love growing PLD films, it's still quite tedious. Imagine to layer these materials, it takes time. It's not a very easy solution. And what instead I would like to propose in this talk is that we can kind of create such similar electrostatic superlattices naturally, because in fact there are these layered ferroelectric materials based on perovskites that form such superlattices naturally. So here we have different systems, Riddleson-Popper, Dion-Jacobson, Orvelius, and Carpi-Galli, families that I'd like to introduce to you. So you can see that they all have in common that there are these perovskite blocks of a variable number n, and they have some intersecting planes that kind of create the special electrostatics. So it can be some rock salt layers, can be some additional alkali ions, or bismuth oxygen, or in Carpi-Galli case, some additional oxygen planes. But essentially, these materials just form spontaneously, and they all have one thing in common, that they tend to have uniaxial in-plane polarization. So in case it would be in the base of the unit cell as you see it now. And the reason why they have in-plane polarization, unlike normal ferroelectrics, like for example BFO, you would have out-of-plane polarization along one of the diagonals. Here, the idea is that these additional layers electrostatically create frustration. So we kind of squeeze in our perovskites in between something that's charged. So if we take an example of this Orvelius family, we will have this bismuth 2O2 layer, and we can break it down to something that has double oxygen plane with a lot of negative charge. And then naturally what the system is trying to do, it will try to make use of these charges to screen the polarization. And we will end up with something like this that has, in-plane polarization only. So that's how material layering itself forces to be polarized in the plane. And today I will mostly talk about the Orvelius family, and hopefully at the end, if I still have time, give you some new data on the Carpi-Galli phases. And I think what was quite important with these materials, that they were for a long time seen as something very complicated to grow, only for ceramics. But in fact, with a good selection of the substrate and growth conditions, we could actually stabilize a really nice layer-by-layer growth mode in the PLD, pulse laser deposition, where we have these minimum of read electron diffraction that we use to probe the growth. That's where we have very rough films, where actually we have these islands of exactly half unit cell in height. And then when we have the high intensity, that's where our films become uniformly flat. So in fact, we don't grow layer by layer of perovskites. We kind of grow full electrostatically neutral units, and then they coalesce to form very nice films. So it means that we can now control our thickness and precision of half unit cells. So we can indeed kind of grow something that's completely flat and only half a unit cell in thickness of these layered materials. In fact, maybe did I forget to tell you the composition? So what I'm working here is the BFTO. So it's bismuth 5, iron, titanium 3, oxygen 15. So it's a layered material that has 4 perovskites and then this bismuth interplane. So that's the material I'll be talking about. So we realized, okay, we can have something that's very nice, uniform, covering our substrate. And we could show that already at 2.5 unit cells, we can have some nice polarization switching in the plane in these materials, good for electric fatigue performance. And most importantly, even at half a unit cell, these materials are already ferroelectric. So this is a lateral piezo response force microscopy, where we're looking at the ferroelectric domains, and we see that already half a unit cell have clear striped domains. Because now, of course, our polarization is in the plane, so it's no longer limited in the same way as the thickness, but it's more limited by the domain width. So our in-plane ferroelectrics, even at half a unit cell, already have polarization. And what's interesting that we have these striped domains where we have head-to-head and tail-to-tail domain walls in the films. Right, so now we have our first component here. We have a film that's very thin and has in-plane polarization. Now let's try growing something on top, like barium titanate, that we know it's out-of-plane polarized. And then, let's see what happens at the interface. Can we actually help to stabilize the polarization in this guy? What we can expect, there are many things. So first of all, of course, there's some minimized stray field. There will be some transfer of polar displacements because we already know the bottom layer is ferroelectric. There will be some available screening charges at the domain walls that will potentially screen it. And quite, I would say, maybe even most importantly, we have to think about the layer polarization, or essentially the charges that we have on the atomic planes. So it's a bit going back to Manu's talk earlier in the morning, where we have LEO, STO, and we have this idea of polar catastrophe. Here, of course, that's not the case, but nevertheless, we have this charge, this continuity that will be happy to screen the BTO polarization on top. So that's another contributing idea here. And how can we probe it? To really see what is happening, we're using optical second harmonic generation during the growth, and we can look at what is happening at this interface. So just to show you a bit, so that's how I grow my PLD samples, let's say. As per usual, we have read, so electron diffraction to monitor unit cell by unit cell growth in thickness, and to know the growth mode. But what's very important that in my lab we had a femtosecond laser coupled in our PLD chamber. So we had essentially a means to probe symmetry breaking. We were looking for frequency doubling of light. So this is SAG. And it's known that this is only allowed when material has a broken center of symmetry. And with the way we select the components we're probing, we know that we will measure a signal that is sensitive to out-of-plane polarization emergence. So having a setup like this allows us to really track polarization at the interface and what is happening in real time. So this is a typical grow of BTO. Here we have just a standard LSMO buffered STO, so a very normal growth done in our lab for many years. So you see that it takes, so this is the beginning of the growth, and then the thickness is increasing, and we're following the signal. You see that it takes around 2 nanometers, maybe a bit less, for the signal to come up, suggesting that this is the dead layer, right? Now instead, let's take the same BTO, same everything, but let's put it on BFTO, the layered in-plane polarized material that I told you about. And now you see it's a bit similar, but kind of different. So first of all, from the SAG light anisotropy, we can see that the material is unchanged, still the same domain state. But what we can see that, of course, if you zoom in, now it's clearly from the very first unit cell, we have a shoot up in our SAG signal, suggesting that actually, even though, surprisingly, this is not metallic, this is insulating, but having this polarization continuity, or we like to call it in a fancy way, flux-closure, that we can indeed have no critical thickness for electricity on even as thin as half a unit cell in-plane polarized BFTO buffer. And then we went ahead and do some more piezo response force microscopy. So we could identify the stripe domains laterally in this layer and single domain in the BTO layer. We could even switch it reversibly without any electrode, because mostly we know that when the films are thicker, they have these stripe domains, so there will be these carriers everywhere that can come and help to enable the switching. So in fact, it shows that even without an electrode, by just using charge domain walls in the bottom ferroelectric, we can replace what we usually need for switching. So we can replace a standard bottom electrode with that. Then we went one next step. Okay, we had BTO. This is nicely out-of-plane polarized. Now can we go one step further and take a multiferroic that has many domain variants? And that is BFO. First of all, we want to see if we still have no critical thickness, and then can we have some selectivity of which domains and domain walls are allowed, because of course here we have the uniaxial in-plane polarization along one axis, and can we have any selectivity? And BFO, as you might know, if we consider a pseudo-cubic unit cell, it has 8 polarization directions along the diagonals and different domain walls. And now we do the same SAG experiment, and once again, same result. We can see something already from the first unit cell. So it seems that this is a universal approach to zero critical thickness in such out-of-plane polarized perovskites. We can see that it's out-of-plane nicely polarized. We can reversibly switch it with an AFM tip. So all looks good. Now let's look into domains. So in the in-plane measurements of the PFM, we can see that we have 2 domain variants. So in fact, okay, we already knew that it's pointing downwards. And out of 4 remaining components, we know that we only have 2 components left. And these are polarization components that actually are they're collinear to the BFTO polarization below. So it's like looks at the strain, and also the electrostatics is somehow enforcing this very unusual selection of ferroelectric polarization variants and domain variants. What was very surprising, in fact, that okay, we have these 2 domain variants in plane in BFO, and we noticed that actually at every domain wall, especially whenever it was head-to-head and tail-to-tail charge domain wall, we started seeing some unusual signal in vertical PFM, which looked a bit like spaghetti, was a bit strange at first. We did a lot of tests to really confirm it's not some spurious artifact. And indeed, it looks to be that there's some out-of-plane component coming up exactly at the wall. And that, of course, implies some type of ferroelectric rotation, polarization rotation in the plane of the domain wall. So in this case, because of the geometry, we know that these are going to be ferroelectric Néel domain walls. And what's interesting that there's always the same deterministic sense of rotation. So for every head-to-head domain wall, so let's say this guy here, we know that it's going to be down polarized, and for every tail-to-tail domain wall, like here, it will be up polarized. So there's some net chirality in the film, some net preference of how the polarization is rotating in these walls. So in fact, if we now look just at the head-to-head domain wall, here our polarization is going through the downwards polarization. Okay, it's already surprising that there's some rotation because, you know, ferroelectric domain walls, unlike ferromagnetic ones, are deemed to be non-easing, so we don't usually expect any polarization rotation just vanishing at the wall. So that's already surprising. But now if you look at the tail-to-tail wall, it's even more shocking because now it seems to be that our polarization wants to really do this 251-degree detour and go through the up polarization consistently at every wall, suggesting that there is some clear frustration in the system that forces this unusual chirality, or so-called homochirality, in the Néel walls. And we could even see it in our atomically resolved stem. We could see that, okay, we have areas on this tail-to-tail wall that are kind of pointing upwards, left, and some of them are pointing right. So there seems to be some, maybe also you can see this, some strain at the wall and some rotation of polarization that seems to be consistent with this. And once again, just to reiterate the message that in ferromagnets, that's quite well known. So in spintronics, homochiral domain walls are usually stabilized, you know, in ferromagnets by interfacial DMI, and that's usually what enables the unidirectional current-driven motion. But in ferroelectrics, so far, there were not many reports, so it was, I think, only in 2020, 2022, when there were some synchrotron studies picking up on some chirality at the domain walls induced by dense stripe domains, once again in BFO. And in this case, we seem to have something quite similar in the sense that we also see the same homochirality, but here it seems to be induced by this unusual buffer below, unusual strain and unusual electrostatics that we have, and we can even measure in SPM. And that seems to be quite compatible with the electric counterpart to the magnetic DMI that was predicted in 2021 in the theoretical paper. So it seems to be that the measurements are kind of becoming the new interesting thing in ferroelectrics, that we can look for some chirality at the walls as well, not just the magnetic community. And now just a quick outlook that I started in my postdoc a few months ago. We're working on now the Karppi-Gali phases, seeing what they have to offer. And here we have 110-oriented perovskites interleaved with some additional oxygen layers. That's the general structure. And the reason why we're interested in them, because in bulk, it is known that these materials, like if we take n equals 4, 2 to 7 material, it looks a bit like this. We know that when it's not doped, it's very nice, insulating, and ferroelectric, and has a very high TC. But the moment we start doping it with lanthanum, it turns into something that has metallicity along a axis. So far, it's only been shown in bulk, but as you can imagine, you heard already the talk from Manu this morning that polar metallicity is something very interesting and very new, and we were definitely intrigued by the concept of somehow having this ferroelectricity and metallicity coexisting, especially that in bulk it was shown that while it's conducting, the phonon modes and ferroelectric soft modes seem to be surviving, so there seems to be some coexistence, and that was the original motivation. And then again, I went through the same film optimization, and we actually end up with a very similar story than what I showed you for the Aurelius films. So it looks quite consistent through different families. So we could again get these big reed oscillations, stabilize nice layer by layer ferroelectric growth with all the islands being exactly half, or in this case, 1 unit cell in height. And even grow it on different substrates. Interestingly, we could still see the same stripe domains at 1 unit cell, so we have the same ultrathin ferroelectricity, same head-to-head, tail-to-tail stripe domains, so it's very nicely reproducible for different families as well. Of course, when you grow thicker films, we have, again, uniaxial in-plane polarization with 2 ferroelectric components, and we can actually switch quite nicely in the P loops in the plane with some interdigitated electrodes to show that, okay, we have one clear in-plane polarization axis that's preferred. And interestingly, it's even 4 times higher polarization than whatever was reported in the bulk. So the fact that we're trying to grow these films epitaxially high quality is really improving the properties and also increasing the TC hand in hand. So that's already very nice. But now the next step would be to think about this ferroelectricity and metallicity coexisting. So once again, the layered ferroelectric, n equals 4 Karpi-Gali ferroelectric, we know it's insulating and ferroelectric, but its parent phase, 110 oriented ABO3 perovskite, is metallic and ferroelectric. And that's true typically for titanium, niobium, and tantalate compounds. And we can see actually in our measurements that we can have some of this coexistence. So this is a nice film, very, very good quality. We can see that we have these steps that are exactly 1 unit cell height of this big layered material. We can measure that, okay, it's 1.3 nanometers. Nice ferroelectric response in PFM. But now I have some other films to show where now there's some coexistence. So you can see already in topography, you will have some flat areas surrounding these big steps. And if you look at the piezo response force microscopy, you will also see, okay, there are domains exactly where the ferroelectric is, but outside the ferroelectric, we see this noise and some type of conduction. So it looks like it can happen that we can have this insulating and ferroelectric and metallic and ferroelectric coexisting. But of course, then I think the idea is that, to kind of control the switching between these two in a more controlled manner, and that's what I'm working on currently. So the way we want to tackle this is to start with the ferroelectric insulating phase. So we do some XPS, we see that, okay, we have niobium 5+, so only the insulating variant. And then what we do, it's a bit what you heard in the morning already. We deposit some aluminum on top and anneal in hopes that aluminum will collect all the oxygens, form aluminum oxide, and then reduce the film below. And then hopefully we should have something at the interface, which is the conducting parent phase, or at least reduced layered phase. And then in XPS, we can see that, okay, indeed, we have the new 4+ peaks that appear after we put the aluminum capping. And it looks like we also have some metallic behavior, but this is very new data, and we need to look into it more. But it seems to be that the general idea of maybe being able to have this Topotactic-like reaction, starting from something ferroelectric and finishing with something that's conducting, is also possible, clearly with a polar metal in between. So with all that, I'd just like to wrap up. I hope that I could share my interest in these layered, unusual phases of ferroelectrics, that I could show that this could be an approach for zero critical thickness for ferroelectricity, that we can even have electrode-free poling, and design unusual domains and domain wall chirality. And as an outlook, I showed you that these phases could be interesting for polar metals. So yeah, with that, thank you for your attention.